All right, take a look at section 2-4 on page 45 in your book. Title of this section is Continuity and Discontinuity. And the objective here is, given a function, determine points of continuity and discontinuity. Kind of briefly talked about continuity in the previous section when we were talking about that substitution method. And here in this section, we'll formally define what continuity is. To start off, though, let's go back to maybe a simple definition. In fact, this might be the definition of continuity that you walked in with as far as what you think it means to be a continuous function. We'll definitely improve on this definition greatly, though. A continuous function, you may have thought of it this way, though, as a function that can be sketched from left to right on your paper without lifting your pencil at all. You can start on the left side of your paper, start sketching that function, and not have to lift your pencil. You must have a continuous function as a simple definition to work with. We'll start with that, and we'll greatly improve it here in just a few minutes. To do that, we're going to take a look at some functions, some graphs of functions, and we're going to consider whether they are continuous or not, just based on that simple definition. And in particular, I want to look at two things with each of these functions here. I want to consider what's happening with f of c, that is the actual function value itself, versus the limit of f of x as x goes to c. Consider those two things and see what happens here. So let's start out with some discontinuous functions. All right, the two that we're going to start with are removable discontinuity examples. We defined what a removable discontinuity was, or at least looked at graphs that had removable discontinuities. It just meant that you have a single hole in the graph. And it's a removable discontinuity because you can remove the discontinuity by filling that hole. All right, so let's start with just a simple function. It really doesn't matter what the function looks like, but I'll sketch some graph that does this. So I'm going to put a hole in that graph right there. And notice that we indicate that by actually drawing an open circle on your paper. If you actually graph this, there's just nothing there. There's literally just a hole there. But with the way we indicate it is by putting an open circle there. So this right here is the value of c that we're considering. And if you were to name this location for this hole, we'd call that L, actually. And the reason we'd call that L, again, considering the two things that we want to consider here, the limit and the function value, if we found the limit as x goes to c of f of x, we would say that's equal to L. From our previous work that we've done so far, I think we can all agree that that limit is L, even though there's a hole there. So the limit exists, it's equal to L. But the problem that we have here is that f of c does not exist. That seems to be our problem there. The function has a limit, but the function value does not exist. All right, well, we could say, well, we can fix that problem. Let's draw another sketch of a removable discontinuity, but instead of just having the hole there, somewhere, let's say above this, we're going to plot some point. So at x equals c, now the function is actually defined up there at that point. But the problem that we have here, again, if you found the limit, we would say that this is our limit L. If I asked you what's the value of the function, and when you plug in c, you'd get this y value up here. I'll call that f of c, actually. So the function exists, the limit exists, but you can see those are definitely two different y values. That looks like our problem here. I've got the limit as x goes to c of f of x. That's equal to L, and that's definitely not the same as my function at c. It's not the same as f of c. All right, so even if we try to fix that problem here and make this thing continuous, unless I plug the hole with that point that I put in there, I still have a discontinuous function. All right, but those are both examples of removable discontinuities. take a look at two more discontinuities, and then we'll jump into some continuous functions. Let's start with this step discontinuity that you have over on the left here. Now, a step discontinuity, again, we define that. That means your function is either stepping up or stepping down at some point C. So let's sketch our function. I'm going to kind of do the same shape here, although it doesn't really have to be the same shape here. But I'll say we've got an open hole here, and then we step up to, let's say, this point up here. That'll be our function. So this is the point C here that we're considering, where we have a step discontinuity. Now, if I asked you what the function value was, since I actually defined this point right here, this would be f of c. But you can see that the problem that you're going to have here is with the limit. F of c exists, but the limit from the left side and the right side are different. So that means that the limit as x goes to c from f of x does not exist. So there seems to be a problem. Again, my function existed at that point, my limit did not. And that's probably the reason why it's leading to a discontinuity, is what we're trying to see here with comparing both these things. All right, the last type of discontinuity we'll look at is, I guess, a new name perhaps for us, infinite discontinuity. You might be more familiar with the word vertical asymptote is really all we're talking about here. So maybe we've got a function that does something like this. And this is the point C that we're considering here. So at C, we've got this vertical asymptote. Well, now you got problems with both the limit and the function value. The function doesn't exist there because you have a vertical asymptote, and neither does the limit. So the limit as x goes to C of f of x does not exist, and f of c does not exist. You got problems with both of those. All right. Now let's compare that with functions that we know are continuous, again, from our simple definition that we can sketch them from left to right without lifting our pencil at all. So let's start out with let's start out with a function that's still got an interesting little feature to it. And we'll name that here in a second, but let's say it's got a kind of an abrupt change to it. It comes to a point. By the way, we call this a cusp. We'll define that in just a bit, but that's a cusp, a sudden change in direction like that. Let's use that as our point C, though, that we're considering. If I was to ask you to find the limit of that function, that would be that value up there. And if I was to ask you what the actual function value is, it would be the same thing. It's that same y value up there. So in this case, I have that the limit as x goes to c of f of x is the same as my function value at c. So that L is also, I'll put it up here, that's also equal to f of c. That's a continuous function. That looks like a key note here for us, is that when these two turned out to be the same, we had a continuous function. On the previous four examples, we could see that there were differences here. Either one wasn't existing or the other, or when they did exist, they weren't the same. Those cause problems in terms of continuity. But as soon as we have the limit and the function value the same, we got continuity. Let's draw something that's, I guess, just a little bit more straightforward here for us. I guess just a standard function that there's no jumps, there's no gaps, there's no holes, there's no vertical asymptote. Let's just pick some value c here. And again, if I was to ask you to find the limit, you'd say it's this value right here. In fact, if I asked you the function value, you'd say it's the same thing. This is also equal to f of c. So again, with this example, I can see that the limit as x goes to c of f of x is the same as f of c. And again, in those last two examples, when that happened, we had a continuous function. That looks like the key here for us in terms of continuity. We got to look at the limit, and we got to look at the function itself, and consider that function value and the limit and see if they're the same. So that'll lead us to the formal definition here of continuity at a point. So what exactly is our definition? There's a three-part definition here. It is critical that when you're talking about continuity, you talk about it in this sense right here. Don't tell me things about being able to draw something without lifting your pencil. That's not going to work. The formal definition of continuity at a point is this, and this is how you specifically tell me that you either are continuous or you're not at a particular point. Function f is continuous at x equals c if and only if it meets the following three criteria. First of all, the function at c exists. When you plug in that given c value into your function, do you get a number out? If you do, it exists. Secondly, evaluate the limit of your function as x goes to c, and does it exist? If it does, you meet the second condition. And then finally, are those two numbers that you just came up with the same? Is the limit as x goes to c of f of x the same as f of c? And if they are, then you have yourself a function that's continuous at that point. We can extend this definition a bit if we want to talk about continuity over some interval. Continuity on an interval just simply means that you have a function f that's continuous on an interval of x values, if and only if it is continuous at each value of x in that interval. Function f is continuous on an interval of x values if and only if function f is continuous at each value of x in that interval. So you got to consider continuity at every single point in order to guarantee that. At the endpoints of a closed interval, which means that you're not including, that you are including the endpoints, is what closed interval means. At the endpoints of a closed interval, only the one-sided limits need to be equal to the function value. And that's because technically the function might not exist on the other side. Or at least it's not even part of the interval you're considering. So at the endpoints, you only have to consider one-sided limits in order for it to be continuous. The one sketch we had there had a cusp in it, so let's define what a cusp is. A cusp is a point at which the function is continuous, but the derivative is discontinuous. You know, we've got an idea of what a derivative is in that first chapter. Dealt with slope, rate of change. So we'll come back to this idea when we cover more details in terms of derivatives. But a cusp is a point at which the function is continuous, but the derivative is discontinuous. Another way of describing that is we would say that it's a sharp point or an abrupt change in the graph. In fact, it doesn't even really have to be that sharp of a point. It could be the case that it just makes a slight bend in the function there, that you're moving along at a slope of 1 and all of a sudden, boom, it changes to a slope of 5 or a slope of 3 even. All right, if there's some change in direction there suddenly without being some nice smooth curve there, you got yourself a cusp. All right, so let's take a look at an example here. If you look on page 48 in your book, example 1. We're going to look at just parts B and C here. Part B says, does the graph of f of x have a limit as x approaches 2? And explain, and then is it continuous at 2? And then secondly, part C is going to ask us about what's happening at x equals 5. So we're basically answering two questions about continuity here at two different points. So let's start with x equals 2. So really the question you're asking yourself is the following. Is f of x continuous, I'll abbreviate that, at x equals 2? Right, that's the question we're trying to answer. So there's three parts we've got to put together to answer that question about continuity. And it goes back to the definition that we just looked at. You have to meet all three parts of that definition of continuity in order for you to say that this is continuous at x equals 2. So the first part of that definition of continuity talks about the function existing. So let's evaluate this function at 2. If I plug in x equals 2 into that function, when I plug in 2 into that function, I can see that this thing is defined. That's that solid point that they've got marked there. That thing is defined, and it corresponds to a value of, I should do that with a dotted line here. What is that? 1, 2, 3, 4, 5, 6. Looks like is where we're at there. So yeah, it looks like f of 2 is equal to 6. So f of 2 exists. Again, as long as you get some number, it exists. So it meets the first part of the definition of continuity. The second part of the definition of continuity talks about the limit. So we got to take the limit as x goes to 2 of f of x. Oh, here's where we're going to run into a problem. Limit from the left side, I can see is headed towards 6, but from the right side, it looks like it's headed towards 4. Those are not the same. So this limit does not exist. In fact, that happens every time you have a step discontinuity, right? Limit from the left side and the right side will always be different, and so therefore the limit will not exist. So as soon as we find something that's not true there in our definition of continuity, we can stop. I don't need to check the third part of the definition because I didn't even meet the second part of it. So I can then state, therefore, f of x is not continuous at x equals 2. And you should have some concluding statement you can put on the end of that. All right, that's continuity at, or checking for continuity at x equals 2. Let's do the same thing, but check for continuity at x equals 5 is the second question they're asking us here. So is f of x continuous, I'll abbreviate that again, at x equals 5. And again, there's 3 parts to this definition, so I got to check all 3 parts. First thing I can do is find out does f of 5 exist? If I look at what's happening at 5, that's right here. Looks like f of 5 is approaching this value, or not approaching, it is that value right there of 7. So we can say that f of 5 is equal to 7. F of 5 is equal to 7, which means it exists. So it meets the first condition. Again, I got some number. Second part of the condition, of the definition, is the limit. So I got to consider what the limit as x goes to 5 is equal to. And it looks like, in this case, as I approach 5 there from the left side or the right side, looks like in both cases they're approaching this value of 7. So the limit is 7. So that means it exists. So we've met the first 2 parts of our definition. And now the third part is just to check to see whether those 2 things are equal to each other. And the limit as x goes to 5 of f of x we said was equal to 7. And that happened to be the same thing as f of 5. So it meets that third part. It meets all 3 parts of the definition of continuity. So therefore, f of x is continuous at x equals 5. All right, again, make sure you go back to the definition of continuity to explain why you are continuous. And our definition I'm talking about is this formal definition, not the simple definition we started off with. That was kind of our way to get started, but now that we've got a formal definition, that's what we fall back on, is this guy right here. All right, that right there is the end of the first part here of section 2-4.